USB 3. The Superspeed Evolution, a deep dive into USB 3. The transition from USB 2 to USB 3, released in late 2008, marked one of the most significant architectural overhauls in the history of peripheral connectivity. While USB 2 had successfully unified the world of keyboards, mice, and basic printers, the digital era was rapidly evolving. High-definition video files, massive system backups, and the advent of solid-state drives, SSDs, were pushing the 480 megabit per second limit of USB 2 to its breaking point. USB 3, marketed as Superspeed USB, didn't just tweak the existing technology. It introduced an entirely new physical layer and protocol to handle the data-heavy demands of the modern world. The dual-bus architecture. To understand USB 3, a technician must first understand its dual-bus design. While the goal was to create a faster connection, the designers at the USB Implementers Forum, USBF, knew that backward compatibility was non-negotiable. Users wouldn't adopt a new port if it made their old thumb drives and keyboards obsolete. To solve this, a USB 3 cable actually contains two separate sets of wires working in parallel. The first set is a standard USB 2 legacy bus, consisting of the same four wires we've seen before: power, ground, and a differential data pair. This ensures that if you plug an old USB 2 mouse into a new USB 3 port, it operates exactly as it always has. The second set is the Superspeed bus. This new architecture adds 5 additional wires, 2 dedicated for transmitting data and 2 dedicated for receiving data, plus a separate ground for signal integrity. By separating the talk and listen pathways, USB 3 achieved full duplex communication. Unlike the half-duplex USB 2, which, like a walkie-talkie, required one side to stop before the other could speak, USB 3 allows data to flow in both directions simultaneously. Bandwidth and throughput, the 5 Gbps barrier. The headline feature of USB 3 was its massive leap in raw speed. While USB 2 topped out at 480 Mbps, USB 3 introduced a theoretical maximum bandwidth of 5 gigabits per second, 5 Gbps. This is a nearly 10-fold increase in speed. However, as any seasoned technician knows, there is a difference between transfer rate and usable bandwidth. USB 3 uses an encoding scheme called 8B10B encoding. This means that for every 8 bits of actual data sent, 10 bits are physically transmitted. The extra 2 bits are used for error correction and signal stability. Because of this 20% overhead, the actual usable data rate is closer to 4 Gbps. Even with this overhead, USB 3 turned a 15-minute file transfer into a 90-second task, making external storage a viable alternative to internal drives for the first time. Physical changes and the blue connector. Because USB 3 required 5 extra wires, the physical connectors had to change. To help users identify the faster ports, the industry adopted a standard color coding system: blue. In almost all cases, a USB 3 port on a motherboard or a laptop is molded in blue plastic, Pantone 300C, while the cables themselves feature a matching blue insert in the connector. The Type A connector. The standard rectangular plug remained the same size, but if you look inside, you will see 5 extra, hidden, pins tucked deep into the back of the connector. These pins only make contact when a Superspeed cable is inserted. The Type B connector. Because the 5 extra wires couldn't fit into the small square profile of the traditional Type B plug, engineers added a top floor to the connector. This makes USB 3 Type B plugs look taller and distinctly different from their predecessors. This is a one-way compatibility. A legacy USB 2 Type B cable will fit into a USB 3 printer, but a USB 3 cable will not fit into a USB 2 device. The Micro B connector. This is perhaps the most recognizable USB 3 change. To accommodate the extra wires on mobile devices and portable hard drives, the connector was widened into a dual-chamber design. This is common on external, passport, style hard drives, and certain older smartphones. Improved power management. USB 3 didn't just move data faster, it moved power more intelligently. As we noted with USB 2, the 500 mAh limit often left devices struggling for energy. USB 3 increased the power output of a standard port to 900 mAh at 5 volts. This 80% increase meant that high-performance external drives no longer needed those clunky Y cables to draw power from 2 ports simultaneously. Furthermore, USB 3 introduced a much more efficient way for devices to sleep. In the 2 era, the host computer had to constantly poll or check in with every device to see if it was still there. In USB 3, the devices themselves can send a signal to the host to initiate a low-power state. This was a critical advancement for laptop battery life, as it allowed the USB controller to sit idle until a peripheral actually aided to perform a task. The naming confusion, 3.1, 3.2, and Gen 1. For a technician, the most frustrating part of the USB 3 legacy isn't the hardware, it's the marketing. As newer, faster versions were released, the USB-AF decided to retroactively rename older standards. USB 3.1 Gen 1 is exactly the same as USB 3, 5 Gbps. USB 3.1 Gen 2 doubled the speed to 10 Gbps. USB 3.2 Gen 1 is, again, just the original 5 Gbps standard. USB 3.2 Gen 2 X2 refers to a modern 20 Gbps standard. When a technician is troubleshooting a slow connection, they must verify the exact gen of both the port and the cable. A 5 Gbps cable plugged into a 20 Gbps port will still only run at 5 Gbps, as the bus always defaults to the slowest link in the chain. Signal integrity and cable length. The increase in frequency required to hit 5 Gbps brought a new challenge: signal attenuation. Light travels through glass for miles, but high-frequency electrical pulses in copper lose strength very quickly. While USB 2 cables could reliably reach 5 meters, USB 3 is much more sensitive. To maintain superspeed performance, most USB 3 cables are limited to 3 meters, about 10 feet. Beyond this length, the electrical noise and resistance of the copper cause the eyes of the signal to close, leading to data errors. For situations where a longer run is required, technicians must use active cables, which contain a small chip that regenerates the signal midway through the wire. Summary of the superspeed shift. USB 3 was a masterclass in transitional engineering. It provided a massive bandwidth boost and superior power delivery, while remaining perfectly compatible with the billions of USB 2 devices already in circulation. It moved the industry from a half-duplex, host-polled architecture to a full-duplex, asynchronous system that could finally keep up with the speed of flash memory and high-definition video. For any IT professional, mastering the physical differences in connectors and the nuances of the Gen 1 versus Gen 2 naming schemes is essential for maintaining modern computer hardware.